Okay, so welcome to week 10, day 1, part 2 of the lecture. Today we're going to be talking about pointers. So pointers are one of the least favorite parts of C and C++. Um, they're, however, necessary. They're less necessary than they used to be, but they're still necessary. So we're gonna learn those today. So let me delete code from the previous class and get going. So we talked a little bit before about the memory model. If you make an array like this in C++, this is what's called a stack allocated array. So it's going to eat up 400 bytes of memory on the stack. If you want to heap allocate the memory, then the heap, if you recall, anytime you allocate something on the heap, it's permanently allocated, and you can do it like this. Int array2, I guess, equals new array 100. So this is a heap allocated array, 400 bytes off the heap. Now, these two things are going to look very new R. New int, how about that? Okay. This is going to do something very similar. So R and R2 are, for a lot of, purposes, they're exactly the same. You could say like array 20 is equal to 9,000. You could say array 2, 20 equals 9,000. For all intents and purposes, these things look very similar. So you might be like, well, so what is the difference? What's going on here? What's the difference between the stack and the heap and all this kind of stuff? Well, the stack is small. Okay, the stack, if we're talking about, let's say 40 memory model, you guys remember this? The stack is, maybe 80 megs, 100 megs, something like that. Your modern system has like 32 gigs of RAM, and stack is like 80 to 100 megs. It kind of depends, but that's kind of the order, something like that. And the nice thing about stack allocated variables is that this guy here will automatically get cleaned up when main ends. So if I had a function up here called like add, and it makes an array of size 100, and we're gonna, I don't know, sum is equal to 0 for int I equals 0, I is less than 100, I plus plus, sum plus equals ri, cout sum. Because this is stack allocated, this automatically gets allocated and deallocated. It means memory is reserved for it when you call this function. When we come down here and we call sum, this is going to, sorry, not sum, add. No, let's call it sum. Why not? When we call this, it's going to allocate 400 bytes of memory. 100 integers is 400 bytes, because each integer is 4 bytes. It'll automatically allocate 400 bytes of memory, and then when the function returns, it deallocates the 400 bytes of memory. Everything's cool. The trouble is, like, the stack is small. Okay? And it would work fine for this, but if we were to make this like, 1 million in size, then, or add another 0, then you get a segfault. Okay? So you can't make arrays that are bigger than the stack limit. It'll segfault. So you have to switch over to heap allocated memory like this by using new. Now, the new command is new for today. So what new does is that this allocates memory off the heap instead. So if we look at our memory model over here, the heap is down here and it grows upwards, and the heap is 2 gigs in size. The stack is 100 megs, the heap is 2 gigs. It's much, much bigger. Okay? And so if you're making a small array, yeah, sure, a stack allocated array is fine. But if you're going to be making a big array that's like 100 million elements in size, that is now not 400 bytes. This is 400 million bytes. It's 400 megabytes. Okay? This is too big to fit on the heap, or too big to fit on the stack, so we have to fit it on the heap instead. Okay. The other important difference: stack is small, heap is large. That's one difference. Another difference is stack is fast, heap is slowish. It's not that slow, but this is very fast to do. Making 100 integers very fast. If you use new, it would be slower. It's not that slow, but it's slow. And then stack is temporary, heap is forever. So what does that mean? If we switch this code out with this int pointer r equals new int 100, and every time we call this function, it's going to be allocating 400 bytes of memory off the heap, and they don't get deallocated automatically. Okay, these automatically get deallocated. This lasts until you give the delete command. So if I wanted to write my code properly, I would say delete the array. This deallocates R. Okay. There's a rule in C++ that says every new needs exactly one delete. All right. And the modern way of coding is to have no news at all. So the modern way of coding is to say no news is good news. And so we use vectors instead, because vectors, you don't have to worry about any of this nonsense. The vectors will handle the memory management for you. So why do you need to know this? Because other people still use arrays. And if you don't know this, you're going to be confused when your code is crashing and segfaulting and things like that. And it's not even your fault. It's the other guy's fault. Right? Just use vectors. Yes, that's the correct answer. But the rule here, and you have to know this, because when you get to 41, you have to know new and delete. Like for CSI 40, you can kind of like not worry too much about new and delete. You're going to worry about it till today. You're mostly not going to need to worry about it until you get into 41 and start doing data structures. So, but the rule for today, learning point number 1, is every new needs exactly what happened here. Every new needs exactly one delete. Yep. So this code here is balanced, as all things should be. There's one new. This will allocate room for 100 integers off the heap. And then we're adding up a bunch of uninitialized memory to see what we get when we add up uninitialized memory. And then we delete it. This code is perfect. Chef's kiss. This is correct code. Okay? And do you guys get what we're doing here, by the way? So this array is not initialized. Okay? This is just uninitialized RAM. And then we're going to add up all the numbers that are uninitialized and then print the result. So we're finding out what happens when you initialize uninitialized, when you add up uninitialized arrays. I probably should do something like this. Const int size equals 100. And do size here instead of 100. This is more proper code here. Mm-hmm. My coffee is coming. Not quite here yet, though. Okay. So we do this so that you don't have those magic numbers all throughout your code. All right. We have this so that it's all the same thing here. And we just run this. So we can like run this code, command, compile, run, and we got 0. Are we guaranteed to get 0? What do you guys think? If 64 gigs of RAM, you're fine. Oh, let's find out a second. So are we guaranteed to get 0 here? What do you guys think? If we add up uninitialized variables, are we guaranteed to get 0? Or are we just lucky to get 0? Or are we unlucky to get 0? Yeah, it's not guaranteed at all. Okay. And if I were to like, I don't know, switch this out, and maybe, so I'm switching from like a static allocated array to I'm switching from a heap allocated array to a stack allocated array. Maybe we could do something like this, while true sum. Okay. So it's going to be calling this code sort of an infinite number of times. We'll see if we always get 0 or not. Look at that. We didn't get 0 that time. That's for sure. If we switch it back from stack allocated to heap allocated, then we're getting zeros this time. Again, there's no guarantees. If I turn off the optimizer, I'm still getting zeros, but again, no guarantees. All right. So, okay. So every time you have a new, you need to delete. Now, what happens if you forget to do the delete? Like some code I was looking at last week. A student was sharing me some homework assignments that he was given from another class, not at our school, but some other class. And the professor had news, but no deletes in their code. So his code was doing what's called a memory leak. Okay, so learning point number 2: if you don't delete, you memory leak. All right, and so memory leak is not actually the worst thing, but every time we call this function now, we're allocating 400 bytes of memory. We're using it, and then we're just returning. And so that memory is now gone. That memory's been allocated. It can't be recovered. The only way we can recover this memory is by Control-C, quitting the program. The only way you can ever recover memory from a memory leak is to actually just quit the program entirely. Then the operating system comes in and wipes, basically drops a nuclear bomb on your program and recovers all of that RAM. This is not a good way of programming. That said, it doesn't cause a crash until you actually run out of RAM. And I'm not going to run out of RAM allocating 400 bytes at a time. You know what I mean? So, Crash Bandicoot, right? So if I were to compile this code and run it, you'll see it's not crashing, right? Because it takes actually a really long time to run out of gigabytes of RAM, 400 bytes at a time. So even if I were to make this bigger, like let's say we're going to be allocating we're going to allocate 4 megabytes per loop. This will run for a while before it runs out of RAM. Okay. And I can even pull up a session over here. Snap that over and put htop. And so this is the RAM consumption on our server right now. And I'm going to run this program, compile. And this is our CPU usage. This is our RAM usage. And if I run it, watch what happens. I'll move my face over here. See that? So we're adding 101 CPU time. Memory consumption is now creeping up. You see that? We're at 100% RAM. Consumption of RAM on the server is just going up and up and up. Memory usage 1.5%, 1.7%. And if I let this run for a while, you will see that it will eventually run out of RAM and die. Oh, you guys don't want to wait for this? Okay, fine. Are you actually waiting? I don't know. It's going for a while. Okay. It'll eventually run out. So here, let me accelerate the process. Let's do 400 megabytes per loop. This will make it go pretty quick indeed. Did I recompile? No? And maybe I should do this without the optimizer turned on. Anyhow, so what I actually wanted to show you was fsanitize equals address. Okay. And so there's a tool called Address Sanitizer. And Address Sanitizer will actually tell you, it's got to be a way to incorporate this memory. Yeah. There's got to be a way to incorporate this memory filling up tension into a horror game. Yeah, like Firefox. Firefox had a memory leak in it for like 10 years. And so you would open up Firefox and its memory usage would just keep kind of creeping upwards. And after you'd had Firefox open for a week, it was eating up like all of the RAM on your system. You just had to quit Firefox and relaunch it, and then all the RAM was recovered. But there's a great tool called Azure Sanitizer. And Azure Sanitizer will tell you where bugs in your code are. So here we go. Look, we're not getting zeros now. Oh, Control C. That won't work. Let's make this like a for loop for anti equals 0, I is less than, I don't know, 5, I plus plus. So 5 times we're going to run this thing, and we're going to leak memory 5 times. So here we go. With Address Sanitizer turned on. Thank you very much. Yeah. 2, 3, 4, 5, and there we go. Thank you very much. So with Address Sanitizer turned on, you can see it gave us a leak. So Leak Sanitizer said, we have detected a memory leak. So what happened was we allocated memory, but we didn't deallocate it. And we've lost a total of 2 gigs of RAM and 5 objects allocated. So 5 times we allocated memory. We leaked a total of 2 gigs. Where did you leak it? In some, I need to turn on debugging in order to get useful error messages here. Run 1, 2, 3, 4, 5, and bloop. There we go. So if debugging turned on, it tells me main.cc line 16, the colon 16 there, tells me which line I was leaking memory on. So I can go into line 16 like this. If you vim something with plus 16 at the end, it will open up line 16, and it will show you exactly which line you have a new that does not have a matching delete. It's like the rule of the Sith in Star Wars. For every master, there is an apprentice. Okay, it's the rule of 1. For every new, you need a delete. For every master, you need an apprentice. Okay, that's just how it is. So, yeah, the thing is, like, I don't know why, but like a lot of people have just never heard of Address Sanitizer. Like, I have students that go all over, the state, I guess over the world, country, whatever. And like wherever they go, like people have just never heard of Address Sanitizer, and it's just so useful. You just run your program and it tells you if you screwed up. It runs slower, like you saw how much slower it ran there. Like this 1, 2, 3, 4, 5, right? Versus like if I compiled it with no Address Sanitizer, everything else being the same, 2, 3, 4, 5. Like you can see, it's noticeably faster to not have Address Sanitizer on, right? Like it does slow you down. That said, it's really nice to just get a report saying, hey, you screwed up 5 times. You called new on that line, and you leaked this much memory across 5 allocations. It tells you this thing was called from here. So line 26 of main called line 16 of main, where you called new. You don't have a matching delete. Boom. It is so nice. It is so very nice. Now, what if you do the opposite? What's the problem with this? We got 1 new and 2 deletes for new. What's the problem here? Too many deletes, right? You need rule of Sith, right? You have violated it. So if we compile this code without Address Sanitizer on and just run it, we get a seg fault. Okay, not very useful information, right? Hey, your code crashed. Okay, where? Right, where did it crash? Could you tell me? But if you were to compile this with Address Sanitizer on, fsanitize equals address, and let's turn debugging information on too, because that's always useful. -G, it's debugging information. Run that. Then, voila, you actually get a useful error message here. So, Address Sanitizer, deadly signal. Error, Address Sanitizer, segmentation violation on unknown address. The signal is caused by a write memory address. Sanitizer, atomic, compare exchange, strong. who cares? What we care about is right here. That's where you crashed. You crashed in file main.cc, line 22. Okay? So I go into vim, main.cc, line 22, and there is our problem child. Okay? Deadly Signal. Sounds like a JRPG from the 90s. Yeah. So, Azure Sanitizer is amazing stuff. It can find all sorts of problems. Let's say that we've got new, we got delete, but we're just going off the edge of the array. Let's say. Bloop. Azure Sanitizer catches that too. Heap, buffer, overflow. See, that's why I told you guys it's important to know what the stack is and what the heap is. Right? Even if you're going to be like using like vectors to like do all your memory management stuff, you will get error messages like this and you will be baffled. You will not understand what they mean until you've had this lecture here. Okay? This lecture here is not so that you can be necessarily using new and delete, because for this class you shouldn't, but because other people's code does, and also a lot of the error messages have terms like this: heap, buffer, overflow. Okay, so what happened here was that we had an array on the heap and we went out of bounds. So it was a heap, buffer, overflow. We went over the end of the array. And it tells us it's in function sum in main.cc, line 19. And so if we go into main.cc, line 19, you can tell us this line right here was where we went out of bounds. Okay. And so then you have to do things like look at the value of I and look at the size here and see if you can figure out why the thing is out of bounds. Okay. What is a sudo command to download Azure Sanitizer? It's part of the compiler. You don't need to do anything. So if you have Windows Subsystem for Linux at home, sell it, then you have Azure Sanitizer built into it already. It's also built into Visual Studio as well. And so the command, again, is this. So compile your code this way. If you're ever curious, I've got all this stuff set up for you guys actually automatically. So if you ever want to know what all these commands are, from your account, you can type alias g++, and it will tell you all of the command line parameters I have set up for you guys. There's a lot, okay? So I use all warnings, extra warnings turn into errors. I turn off warnings for unused variables and unused parameters because those are kind of silly and annoying. We compile in C++20 mode. We have debugging turned on by default. We only show one error at a time by default. Once you have an error, it doesn't keep going. It stops. It turns on the debug version of the standard library. It turns on the undefined behavior sanitizer, and it turns on the address sanitizer, which is the, as I said, amazing tool developed by Google several years ago. And like I said, it's just baffling to me that like not more people know about it and not more people use it. It's really, really good. And so if you were to just copy this file or this alias, I guess, all these things can be found in your CSHRC file. CSHRC. So inside of your CSHRC file, you can see all these different aliases that I've set up for you guys. You just copy this over into your WSL installation at home. And now you will have the same command line parameters that you have on the server. So it'll turn on Azure Sanitizer, ubisan, the safer version of the standard library, all the warning settings that I like, that kind of stuff. Debugging's turned on right there. So some pro tips right there. You need to make an alias, yeah. Yeah, and it's funny, like I said, like, you know, I have students that are in other professors' classes, not here, I'm not casting shade at one, but somewhere. And they compile their code with Azure Sanitizer turned on, and then they get all these memory leak errors, and they're like, what am I doing wrong? It's not them. It's because their professors are leaking memory in their code. And then Azure Sanitizer is yelling at them and saying, hey, you're leaking code. I'm like, oh, it's not me, dude. It's my professor that's doing it. And so a lot of other people's code that I've used over the years have had memory leaks in it. And so that's the only real downside to Azure Sanitizer, is that it picks up problems that you inherit from other people. You know, and if you're joining in on a large project, and you're like, hey, do I have a memory leak? It's like, yes, you do. You have 9 million of them. You're like, it's way too many for me to change, you know? So it's good to just integrate Azure Sanitizer into your workflow from the beginning. So you just get into the habit of never having any memory leaks at all. Okay. So again, the rule, 1 new, 1 delete, and you're good to go. Okay. Got time for one more thing with pointers today. So let's shrink this down to size a little bit. 40 bytes. Okay, 40 bytes. Every integer is 4 bytes. So if we make a array of size 10 of integer type, it's 40 bytes. Cool. Let's not stack allocate anything. We're just gonna keep allocate some stuff. Okay. So let's learn a new standard library function called iota. We're gonna iota from array to array plus 10, starting at 100. And so this is going to require us to hashtag include numeric. So what iota does is, well, I'll show you. Okay. So I'm doing all this stuff. I'm doing all this stuff. Let's just print out the array. So for int I equals 0, I is less than size, I plus plus. C out array square bracket I double left arrow n1. Okay. So this is going to allocate 10 integers. This is going to iota them, whatever that does. Anyone want to place bets on what iota does? Vote now in Discord. And then this is just going to print out the array. And then we deallocate the array and quit. So maybe we shouldn't call it sum anymore, but whatever. It's Morbin time there. Okay. Anyone want to take any guesses on what iota does? You want to just see? Okay. So iota fills an array with increasing numbers. Okay. So if we iota from the beginning to the end, starting at 100, it fills in the array with 100, 101, 102, 103, up to 109. It's nothing that you couldn't do already with a for loop. Okay. It's just a nice little standard library function that will fill arrays with increasing numbers. So let me show you something else you can do with a pointer. So a pointer is a memory address. So this thing here, int star, means it holds the memory address of a block of RAM, basically. Okay. So when we say new int size, it's going to allocate 40 bytes of RAM, and it returns the memory address of the first one. That's what int star r means. Okay. This is not an integer. It's the address of an integer. It's the address of the first integer in the array. And if you remember how we could use iterators, we could pass in begin and end, like vector begin, vector end. We can actually do the same thing here, except instead of vector begin, we just pass in the pointer, because a pointer and an iterator are pretty much interchangeable for a pretty big chunk of the time. Any standard library function that takes a iterator, like if you remember how to sort something, right? You just say sort. That works fine. And so we pass in a pointer, iterator, whatever you want to call it, as the first parameter, and then for the ending parameter, we pass in array plus 10. So array plus 10 is every time you add 1 to an array, it points to the next element in the array. So let me demonstrate that graphically for you. So if you have a array here named R, and it's got like 10 elements in it. Let's say dot dot dot. Okay. So we've got array square bracket 0 is the first element, square bracket 1 is the second element, square bracket 2 is the third element, all the way up to square bracket 9. If you have 10 elements in an array, square bracket 9 is the last one. And then this one is like outside of the array. Okay. So R is pointing to the exact same thing as R square bracket 0. These two guys are both kind of the same thing. Okay. R square bracket 0 is going to actually be the value here, which is 100. R is pointing at the address of 100. This guy after it. So when we say R plus plus, no, let's not do that. Let's make a new pointer. So let's do this. Get pointer Bob equals R. Bob is pointing at R square bracket 0. So if you ever want to print out the value there, you can use the unary star operator. If you remember that from last time when we were working with min element and max element and things like that, anytime you have an iterator pointing at a spot, you can get the value at that spot by using the star operator. And so if R square bracket 0 holds 100, what is this going to print to the screen here? What do you guys think? It's going to print out 100. Okay. Very good. Very good. You all got it. So that's Bob right there. Okay. Little note there. Okay. So Bob, so visually we draw it like this. We say Bob is pointing out the thing, same thing that R is pointing to. Now, Bob plus 1 is this guy. So if we were to dereference Bob plus 1, what value will this print out? $101. What do you mean by why 10? Like, why do we want to have 10 people in our array? Just to make it small so it fits on the screen. Oh, array plus 10. Yeah, I'm coming to that. So that's anytime you work with the standard library, you have a starting, you have an ending point. And the ending point is always 1 after the actual end. And so array plus 10 is actually outside of the array. It's 1 past the end of the array. So if we were to see out Bob plus 1, yeah, array plus 10, right. That's 1 past the end of the array. So you see Bob plus 1 is pointing at element 101. Okay. And you could also just say, like, you could write a loop where you do like Bob plus plus, right? So you say Bob plus plus, then Bob would go from pointing to here to pointing here, you Bob plus plus again, points to here, you Bob plus plus again, and points to there, Bob plus plus to there. And this is actually a weird for loop that I don't usually write, but I've seen it very commonly used at places like Berkeley. I don't know why, but let me show you a way that we could do this for loop here to print out the array using that method instead. So I'm going to say for integer pointer Bob is equal to the array, as long as Bob is not equal to array plus 10, array plus size, let's say. Yeah. Size as well. Bob plus plus. Cout star Bob. So this for loop here and this for loop here are exactly the same thing. So what we're doing is we're creating Bob. Bob is going to point at the first element in the array. Is it pointing at array plus 10? Nope. All right, print it out. Print out whatever's here. It'll print out 100. And then Bob plus plus. When you do a Bob plus plus, Bob is now pointing at array plus 1. All right, is that Bob plus 10? Nope. All right, move on to the next one. Prints that one out, prints that one out, prints that one out, prints all the ones in between, prints out 109. And this, to answer your question, Sally, is why we don't say array plus 9. This is how we know when we end. So array plus 10 is the end zone. It's the signal value. It's the guardian. When you get there, you never print the value. That's when you stop. So you stop when you get to array plus 10. So you continue until Bob is equal to array plus 10, and then you stop. You don't print that value out. That would be bad. That's a segmentation violation, right? Maybe. So definitely out of bounds error. Yep. Do you see that, Abdul? That you continue going until you're off the edge of the array, and then you stop. You don't actually print the value there. You with me? So if we were to compile this code, and run it, we get the exact same answer as before. This code and this code are exactly the same. Am I expecting you to write code using a pointer-based loop? No. Do I expect you to at least be able to like recognize it because out there in the world it's going to be there? Yeah, you should at least be able to recognize what's going on here. So this style of for loop you will also see a lot more of in CSI 41 with iterators instead of pointers. But iterators and pointers are conceptually pretty much the same thing. There's under the hood, there's different things going on, but pretty much you can think of an iterator and a pointer almost as if they're the same thing. They point at things. And that's why their type is int star. This isn't an integer, it's an int star. It's a pointer to an integer. And so Bob here points to things. And so if you want to get the actual value of them, that's why you have to see out star Bob. You see out star Bob, that gives you the value that Bob is pointing to. And so Bob will just point to different elements down the list. I'm pointing at you, I'm pointing at you, I'm pointing at you, I'm pointing at you. And we're just printing out, okay, what is Bob pointing at now? 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 In our code here. That's what the star there does. So Bob is not an integer. It has a memory address. Whenever you see this, it's a memory address. It's a spot in RAM. And you can do things like plus plus to go to the next thing in the memory. If you say plus 10, then that will point 10 elements later. Arrays and pointers are basically identical things. Like here we have a pointer, but it's holding an array because pointers are arrays and arrays are pointers more or less. They're pretty much identical, pretty much each other. And so we can copy the memory address of array into Bob and keep going until we hit array plus 10. Oh, all right. So Barbarossa, you're asking why plus 10, right? So we're going to go until we hit array plus 10. And once we hit it, we stop. So we continue until Bob is equal to array plus 10. Once Bob is equal to array plus 10, that ends the loop. Yep. It's basically a range-based for loop. In fact, this is what a range-based for loop is, more or less. So when you do a range-based for loop, it actually will convert it into essentially this. But pointers are considered horrible and scary. I don't think they really are. There's like an extra level of indirection. Like you can't just print Bob. I mean, you could. Do you want to see what happens if you print Bob? You're going to get a bunch of memory addresses is what you're going to get. If you do this, you get the memory addresses of everything in RAM. Not very helpful. You can see they're all like 4 bytes apart, right? They're integers, they're 4 bytes each. But yeah, basically what you have here is Bob points at the first element to begin with. Bob starts off pointing at array, and then we print whatever, we print out whatever is there. Prints out 100, Bob plus plus, Bob's now pointing at this person. We print out whatever's there, prints out 101, Bob plus plus, Bob plus plus. Just we'll sit there and print all the way down. And then once Bob points here, Bob is equal to array. This is array plus 10 right here. So array square bracket 9 and array plus 9 are more or less the same thing. So this is array plus 10. Once Bob is equal to array plus 10, we've gone off the edge of the array. That's it. Quit. Stop the for loop. And that's it. That's our class for today. Hope you guys understand that pointers are a little bit weird looking, but they're not really that bad. I don't write loops this way, but a lot of people do, so you kind of have to recognize them. And again, the main thing to remember is every new needs a delete, and every delete needs a new. They match 1-to-1. Okay? If you screw up either way, then you're either going to leak memory or you're going to do a double free, and that's not good. Okay. You'll do a lot more with news and deletes in 41, but for now, just remember Azure Sanitizer is king, and it'll find any mistakes you made, and just use vectors in the meantime. So that's it. Thanks for all for coming out. I'll see you guys on Wednesday. I look forward to reading your reports. Peace.